So today we're going to be going through 8.2. So we're working with graphing linear equations. So we're expanding on what we just covered yesterday, which is just graphing in general. And now we're going to be using, instead of just graphing points, graphing equations and lines that are going to be showing up on these things. So we're going to start with our definition of what is a linear equation, what kind of looks these equations might have. And then we'll expand on that. So all linear equations can be simplified to have the same general formula, which is y equals mx plus b. Now in this instance, we have here x and y represent variables. M and b are going to be constants that will be given to us. So m and b can be integers, fractions, decimals, and in some instances, if we have nothing written in there, even 0. So when we have these, imagine m and b with these equations, they're just going to have numbers in them. But this is our general formula that we have for linear equations. We technically have 3 different forms that linear equations can be written in, but we'll work with those a bit more extensively in Math 72, and I think even a bit later on in this course as well. But this is the main form that we're going to be seeing a lot of these equations in. So one of the big things that's really nice to be able to see, and this generally shows up on the book homework, but it's worth noting all the same, is determining, have I been given a linear equation or a non-linear equation? And so we have a couple examples here. We have a linear equation. Again, it's the form y equals mx plus b, remembering that m and b can be integers, fractions, decimals, 0, positive, negative, whatever. So I have an m value, my first example, of -1/5. I have a b value of -4 in here, and I just have y equals mx plus b. So got that there. Our second example, y equals 2x cubed minus 2, and I've got this cube showing up in here. Our general form for a linear equation does not have any exponents other than 1, an invisible one, showing up in here at all. So while it looks like it's a very similar form, y equals, I have an m x cubed plus b, this cubed in here is what gives it away as being nonlinear. And then our last example that we have y equals 3x. Okay, well, we have y equals mx plus b is our general form, and I don't have any number on the very end out here. Well, this is an example of where our b value could be 0. The mathematical equivalent of nothing is 0. That's where we have that showing up. So while it's a bit of a different take on a linear equation, it still is a linear equation because it follows this general formula that we have here. So moving on to our next part that we have is finding solutions of an equation that has 2 variables. And this is essentially doing a check to see, is this point a solution to the equation that I've been given? And the way we do that, if substituting x and y in our equation, with ab in a 2-variable equation for the respective variables produces a true statement, the ordered pair ab is a solution to the equation and, quote, satisfies the equation. This is our more technical term that we have, or terms that we use to clarify if we have a solution or not. So it's a fancy way of basically saying you're going to be given a point and you are going to be given an equation. And you're asked, is the ordered pair a solution to the equation y equals x plus 1? Or if I had this on the test, I could give you any other equation that you could be using, and all you are going to do is plug in x and y in for x and y in the equation. So with our 2 examples that we have here, our first one, we have an x value of 4. So first line of work, and I highly recommend to everyone when you are going through and doing these, write out these first 2 lines of work. Write out the original equation, and then directly below that, write out everything substituted in. Do not do any calculations. Just write in the substituted values in for their respective variables. I cannot tell you guys how many people I see that try and substitute and do something and calculate something all at once, and people miss points on that. So do these two lines of work, the original equation, and everything substituted in, and then start calculating. So we plug in these values, find, okay, well, 4 is equal to 4 plus 1. Simplify the left side, we get 4. Simplify the right side, we get 5. Well, 4 is not equal to 5, so that tells us that this point is not a solution to this equation, and that's the best we can do. We look at our other example. We're being asked, is the point -1, 0 a solution to this equation? So again, start with the general equation, substitute in what we have been given. We have an x value of -1 and a y value of 0. So your first line of work, or your second line of work, I should say, you're just plugging in 0 and -1 in for x and y. That's all you are doing in this line. Simplify the left-hand side down. Well, 0 just stays as 0. The right-hand side, -1 plus 1, it's going to give me 0. And I find 0 is equal to 0. This is a true statement, and this tells me that the point -1, 0 is a solution to the equation y equals x plus 1. So when it comes to checking for a solution, this is our process. Just plug things in for x and y, and then simplify the left side down, simplify the right side down. If they're equal, great, it's a solution. If they're not equal, it's not a solution, and we move on. That's all we can do. So moving on to our next part of actually graphing an equation with this. So we have our main definition of the graph of an equation. Our definition of this is the graph of an equation is the set of all ordered pairs that are solutions to the equation. So we've seen in our previous example, okay, well, I have this one point is a solution on this equation. But a graph that's going to end up looking like a line with these is every single possible ordered pair that is a solution to the equation. So that's every single point that this equation could create on a graph. So next part that we have, and I think this is a fairly subtle part that goes along with graphing, but it's still worth seeing, is labeling our variable types for an equation. So up till now, we're kind of like, okay, well, y is a variable, x is a variable. Okay, so we just label it that way and we're done. But we do have some formalized definitions of what these variables represent. So y referred to as a dependent variable because its value depends on x. You can also refer to the dependent variable as the output variable, or what is the result going to be. So y is dependent on an x value, and that's where it's going to find the value at the very end from there. X is an independent variable because its value can be chosen independently of the other variables in the given equation. And we often refer to this, again, kind of interchangeably, as an input variable. We can plug in values for x. We can choose whatever values we want. We can't necessarily choose any value that we want for y. It depends on the context of the problem, but that's generally where we get our two differing definitions for these types of variables. Okay. I think it's also really helpful to think of them as the input variable and output variable, especially when we get down to some of these equations down below here when we're being asked what value are we plugging in for an equation, what value are we getting out for an equation, so we know which one is our input and our output. It's just another layer of labeling and organization that we have as we're going through and working with all of these problems and different types of variables in them. So our other important part that comes along with these is that graphs give us two important pieces of information regarding ordered pairs and the graphs that go along with them. If an ordered pair satisfies an equation, then the point in the Cartesian plane, represented by the ordered pair, is on the graph of the equation. And it's essentially a roundabout way of saying, if I have a solution to an equation, like we did up here with number 2, then I know that this point exists on the graph of y equals x plus 1. So it might seem kind of like well, okay, we already figured that out, so what does that really give us in the grand scheme of everything? Well, it helps us get an idea for, is this thing even going to be on the graph of this equation? Is this thing going to be on the graph of the equation that I'm working with? It's just another way of clarifying that, yes, it will be if it is a solution. And then our second part, again, kind of a nice additional detail. If a point is on the graph of an equation, then the ordered pair represented by that point satisfies the equation. It's kind of going back and forth between these of saying, if I know that this thing is a solution, I can put it on a graph. If I can graph something and find a point, then I know that that point is also a solution to the equation. So it's kind of going back and forth between knowing, is this on the graph and is this a solution? So two ways of confirming that I have a solution is a point on a graph, and a point on a graph is a solution to the graph as well. That's just some clarifying stuff that goes on with those. So now we're going to get into some examples where we're actually finding some values that show up in here. So our examples that we have, find a value that satisfies each ordered pair. So it is a solution to the equation y equals 4x minus 2 and is on its graph. Now, as we just established, if we find an ordered pair that satisfies an equation, then we know that that satisfied ordered pair is also going to be on the graph of the equation as well. So we essentially just need to find the missing variable that's showing up in here. So I have these written in using k to represent an unknown. You can and will see other problems on the homework where instead of having k written in, they might leave this as x. Or in our second example, they might leave this k instead written in as a y. The actual variable that it gets labeled as is kind of your choice, or kind of whatever it gets labeled as. Regardless, it is an unknown, and that is what we are going to be solving for. I'll also note that some instances might give us equations that look a bit different than starting with this y equals mx plus b form. That being said, that does not fundamentally change what we are going to do to go through and solve these things. All we are going to do, we use our first example that we have here. We've been given a point, we've been given an equation. The point and the value could be different, the equation could look slightly different, but the process is going to be the exact same. And I neglected to write the first line of work out here, which is a big mistake on my part. You want to write out the original equation you've been given with all the variables and everything given to you. So y equals 4x minus 2. So that should be the first line here. Then you are plugging in the value that you do know and the value that you don't know. I'm using k in this instance, but you could leave it as x. So I plug in 10 in for y, and I'm plugging k in for x. So wherever a y shows up in our equation, I should have a 10. Wherever an x shows up in the equation, I should have a k, because that's an unknown. And now I'm just going to go through and solve this thing for k. And I'll go to the other to the whiteboard, and we'll go through and actually see this in a bit more detail. But that is the setup steps that we have going along with this. Similar idea for our other one. I have been given an x value, and I'm solving for a y value, or an output value. So I'd start with my general equation. I would plug in what I know for that respective variable, plug in what I don't know for that respective variable, and then simplify both sides down to get to our answer. So we'll jump us over to the whiteboard. Oops, I made it here. Yeah, little whiteboard, so we can go through and show this process out. Okay. So our general equation that we had, we were given the equation y equals 4x minus 2. And again, it does not matter what the original equation looks like. They have to give it to you in some way, shape, or form. But the process to go through it is going to be the exact same. So we want to find our input value such that the output value is 10. So again, our process for this, write out the original equation. Then we are going to substitute in what we have been given in the problem for that respective variable. So we've been given a y value of 10. We've been given our x value to be an unknown of k minus 2. So again, your first line of work, write the original equation. Second line of work, just substitute in information that you have been given. Do not try to substitute and solve and calculate and simplify things down all at once. A lot of people make mistakes in trying to condense some of those steps down for themselves. Do not do that if you're not comfortable with that. Take the extra lines of work, make sure you are going through the work, solving this problem correctly and not just quickly. So I'm getting 10 is equal to, not a diamond. There we go. That. And now we're just going to be solving this thing for k. So this has just become a problem that we've been doing in previous sections. So we find that k is equal to 3, and we have our ordered pair answer of 3, 10. And we're good to go there. So we'll take a look at our second example that we had, just for the sake of seeing it. And again, the equation might look a bit different. The numbers may look a bit different, but the process for going through and setting this thing up for yourself and solving it is the exact same thing. Given an equation, I'm plugging in what I know, what I've been given. And now I'm just simplifying both sides before I start solving for k. So simplifying the right-hand side, I've got 4 times 5 is going to give me 20. 20 minus 2 is going to give me 18. So my ordered pair final answer is 5, 18. And end the parenthesis. There it is. So we've just found some ordered pairs that go onto this equation, that work for this equation and graph. And again, be aware, I'll give you just the heads up warning on that front of you will be given equations in different forms than this. You will be given ordered pairs where they might not use k. They may just leave it as x. They may leave it as y. All you are doing is plugging in what you know into the equation and solving for what you don't know. And we're using our process from 3.5 to go through and find that out, or maybe even chapter 4 if we have fractions showing up. Okay. But this is how we are finding ordered pairs based on being given partial information in the problem. So I'm going to jump us back to our notes. We'll get on to actually graphing some of these things. So there's a few ways that we can actually go through and graph some of these linear equations, but we're going to go through one that's it's got a few more steps involved with it, but I'll give you guys some additional information on this accordingly. So when we are plotting a graph, and this is more specifically when we are working with a linear equation, we want to create and label a table of points. For linear equations, you absolutely need at least 2 points to be able to graph them. If you have more than that, 3 or 4 or 5 or 10, That will work also, but the absolute minimum number of points that you need to be able to graph a linear equation is 2. If you do not have 2 points, it is fundamentally impossible for you to graph a linear equation. There's no way you can do it. So when we are going through and doing this and creating a table of points for ourselves, we may choose the independent variables, meaning the input values of our ordered pair, and then must calculate the corresponding dependent variables, the values for those. So essentially our output values. So we choose x values and we find y values. I will give you guys the warning now that you may not choose both an input and an output value for an ordered pair, as you don't actually know if that's going to satisfy the equation. If we looked at our main one that we're going to use here, y equals 3x plus 2, I'd be willing to bet that if you chose a random x value and a random y value and said, well, that's an ordered pair for this graph, it probably wouldn't be. This works with a very, very, very specific set of numbers, very specific set of ordered pairs, and all we want to do is choose half of that and let the graph tell us what the other half is going to be with some calculations. So once we have determined, again, at least 2 points on this graph, we're going to plot each of these points as we calculated them and connect them on a line. I highly recommend that you use a ruler or some sort of a straight edge to do this. It makes life a heck of a lot nicer. It makes the graph look a lot neater. And then we have our graph and we're good to go. So we're going to use and go through our process of doing this with our first example that we have here. So we're told to graph the equation y equals 3x plus 2. So we have a table of points set up here, but we're going to assume we don't have this. We're going to go through actually doing that and then plotting this thing. So we'll jump us over to our whiteboard and we'll go from there. Oops. Okay, here we go. Now it's cooperating. So we're told to plot, make sure I've written down. We're told to plot y equals 3x plus 2. So again, we need to have at least 2 points, 2 ordered pairs, to be able to graph this thing. If you want to have 3 or 4 or 5 when you are creating your graphs, you're welcome to do so. But you absolutely need at least 2. If you don't have that, you can't solve this problem. You can't plot it, you can't do anything with it. Okay, so first thing we're doing, create and label a table of points. Now, this is 100% your choice on how you want to do this. You can either set up your table vertically or horizontally. I'm going to do vertically just because I like working with it vertically and math vertically. So I have my x and my y values. Now again, second bullet point in the notes. We may choose the independent variable's value, meaning we can choose the input values. So between these two, again, as a reminder with this, the x is the input value. So we can choose our x values for these. Y is our output. So we can choose any x values that we like. They could be positive, they could be negative, they could be 0, they could be fractions, they could be decimals, they could be whatever. My recommendation to people, if you're going to do this, generally choose a number or generally choose numbers between -3 and +3, just because they're kind of nicer and closer to 0, and they generally don't make equations too particularly crazy on that front. So I'm going to choose one of my x values, one of my input values, to be -1. I'm doing that arbitrarily, so I have a negative value. And now I need to go through and determine what is its output value going to be. What's the y value with that? So off to the side, I'm going to go through and find out what that value is going to be. So I'm starting with my equation. I've determined what my x value is, which is -1. And then I'm just simplifying that right-hand side down to find out what the y value is going to be. So I have -3 plus 2, y is equal to -1. So now I know that the y value that corresponds with -1 as an input value is also -1. Kind of a happy coincidence that they're the exact same thing, but that's just a coincidence over anything else. So now I need to choose a second x value. And again, doesn't matter if you want to choose a positive, a negative, a 0. I'm arbitrarily going to choose to pick 1. Put a little bit lower here as my input value, just because I feel like it. If you're going through this and you're saying, well, I want to use 0, I want to use 5, I want to use it, you're more than welcome to. Use whatever number you would like. Box that guy there. So our the one that we had, we're doing the same thing. Starting with our equation, plugging in our input value, and now we're just solving this thing. It's 3 plus 2. I'm getting ahead of myself here. Don't rush your process. Don't make my mistakes. Or at least learn from my mistakes. So when I have an input value of 1, I have an output value of 5. So now I have 2 ordered pairs. I have 2 points. I can now plot this graph. So going back to our process yesterday, how do we go through and plot these graphs? Our requirements that we have, we still need to keep those. I'm moving us off to the side, but I'm going to rewrite our 2 points that we have over here so I have a memory of what we're solving or plotting here. Again, I'm only doing this because I'm running out of space. You guys will have a piece of paper with a lot more space on it than I will. Okay, so we have the points -1, -1, and 1, 5. I need to plot that on a set of axes. So just like we did yesterday, I'm going to say, here's my origin is going to be. Let's create our horizontal axes. Let's create our vertical axes. Let's go like this. So I've got positive x direction, positive y direction. Really don't like how this one's showing up here. That's a bit better. I'm now scaling each of my axes. I'm scaling vertically by 1s. I'm scaling horizontally by 1s also. So we have our minimum requirements for creating this graph. We have our axes set up, we have our axes labeled, we have them scaled. I can see if I'm looking at this as someone's work, I can very clearly see which direction is positive, which one is negative. Good to go here. And now we're going to be plotting these 2 points and connecting them together as a graph. So I'm going to be plotting the point -1, -1. I'm going to do all of this in blue, so our graph versus our axes stand out a bit more. So -1, -1, that's going to show up right down here. Again, started our origin, -1 in the x direction, -1 in the y direction. So we have our first point. Our second point is over at 1, 5. So I'm going over 1 in the x direction. I'm going up 5 in the y direction, which has my second point being right there. And again, the little dots that I'm putting in, you do not need to include that in your graph. I'm just doing this so you guys can track where I'm going with this. So I plotted those 2 points, and now I would take a straight edge and a ruler and connect these 2 things together. I'm going to freehand this. This is probably going to look pretty bad, but that's actually not as terrible as I thought it would be. That did, though. There we go. So connect it together, put the arrows on the end, and you're good to go there. When it comes to graphing these things by hand, most instructors are going to be fairly lenient with the graph maybe not entirely 100% line up as a straight line. Do what you can to get it as accurate as you possibly can. Don't just willy-nilly, oh, it kind of goes like that or whatever off to the side. Put some effort and some care into it, and most instructors are pretty okay with it. But this is our process for going through and simplifying and, well, I shouldn't say simplifying, but plotting a graph. So again, we need 2 input values, your choice on whatever that you want them to be. Plot those 2 points on the graph and connect them together with a straight line, and then you're good to go. Now we are going to get into the other examples where we do have fractions showing up in our original equation, because this is one where I think it's a little bit more subtle with how there's a little bit of a trick that we can go with these, but it's a very subtle trick with this. So we're going to work with the instance where we are choosing input values when m is a fraction. And we're back to our general equation. I'm going to jump us to the first page here. M represents the number directly in front of x. So this one right out front here. So how do we choose a value when our m is a fraction? Well, at least let's put it this way. I'm going to give you guys a hint on how you can go through or a tip that can make your life a bit easier as you're doing this. So we still may choose any number to be an input value for the equation. That part stays the exact same. What I would recommend doing, this is to minimize fractions when the m value is already a fraction. Choose input values that are multiples of the denominator. The values cross-cancel, and a whole number is all that's going to remain. Essentially meaning, if you are starting with a fraction in here, and you choose any number at random, you may have a fraction coming out as an answer. And graphing fractions is not the easiest thing to do all the time. We have to do it from time to time if we have no other choice. But if we can avoid doing that, let's try and make that happen. So again, the trick to this would be determine what the denominator is, and then choose input values that are multiples of that denominator. And remember, multiples always start at the number and then multiply up. So you have, let's say, the multiples of 2 as we're looking at here. 2, 4, 6, 8, 10, 12, etc., etc. Let's say the denominator was 5. The multiples of 5 would be 5, 10, 15, 20, 25, 30, etc., etc. So the caveat that I will give you with this is that unfortunately there is no way to guarantee that you can eliminate fractions if both the m and b values, the linear equation, are fractions. It's just an unfortunate reality of that. If the m value is a fraction, we have this trick to use to get rid of that. If the m and b value are fractions, there isn't as much that we can do on that front. We can still go through and pick values and calculate them the exact same way, but we will not necessarily be able to cancel them out, them being fractions, the same way as we would like this. The rest of the process with setting up a table, computing ordered pairs, graphing, all of that remains the exact same as what we just did up above here. So I'm going to go through and give you guys an example, the examples as to why this is. I'll use a couple other numbers in here. But we are going to work with, and I'll show you guys, if we wanted to graph the linear equation, y equals 1/2 x plus 2. we'll jump over to that. Okay. Now again, we can choose any input value that we want for ourselves. So I'm going to set up a table of points. Again, I'd like to set up my table vertically. You guys can do it horizontally if you like to. Regardless, have X and Y labeled, so you know which one's your X values, which ones are your Y values. A lot of people do not label, and subsequently they get incorrect answers and incorrect points from there. So let's go with the instance where we're going to choose, I'm just going to choose an X value at random. I'm going to choose the X value of 1. Again, I want to highlight why you want to use this trick here. So I'm intentionally choosing one that's different from the advice that I gave you. So if I plug this value in, which there's nothing wrong with this, write out my general equation, write out the input value, and now I'm getting 1/2 plus 2. I now need to rewrite that 2 to have a common denominator. So that's going to become 4/2. And if you aren't comfortable with fractions, then might need to go back and review that, how we got to there. And that's chapter 4 for that. I add those together and I get a y value of 5/2. So I have 1 point as one of my ordered pairs as 1 5/2. And now there's nothing wrong with this answer. This is 100% correct. However, I'm just going to go over to the graph to the left here, just as the quick reference. If you're looking at this graph that we've made over here on the left-hand side, it's not going to be as easy to graph that 5's halves, because it's going to be about, so 1, I'm going to use red here for this graph. It's going to be about like 1 and then 2.5, so somewhere right around there-ish. It's kind of hard because you have to eyeball it, right? So there's nothing wrong with having it written in that way. It's 100% correct, but you can avoid fractions altogether if you use that little trick I gave you guys. So our denominator in this equation is 2. So I'm going to choose 2 multiples of 2. So I'm going to choose 2, and I'm going to choose 4. And now I'm going to plug those values in for x. The really nice part about this, again, we'll see the fractions from our m value disappear here. So we have 1/2 times 2. It's going to give me 1. So I have the point 2, 3. Whole numbers, integers, nicer to work with. Our last one that we have y equals x plus 2, and we're choosing an input value of 4. So half of 4 is going to give me 2. 2 plus 2 is going to give me 4. So now, as we're looking at our table that we have over here, we're seeing, okay, well, I have 3 perfectly reasonable, perfectly acceptable ordered pairs that I could work with to plot this graph. Which 2 are going to be easier to work with? And it's probably going to be the ones that don't have any fractions showing up in them. There's nothing wrong with, and I won't mark you off, if you want to use y equals 5/2, or y equals x equals 1, y equals 5/2 for your ordered pair. Nothing wrong with it. It will work. But if you start getting, let's kind of take a step back from this and think to fractions in general. 5/2 is a pretty nice number. think it gives us 2.5. What if we start having some really, really gross fractions showing up in there? Maybe 13 over 7. Maybe 25 over 8. Maybe we have 163 over 57. These gross combinations. They're not as easy to graph if the fractions get a bit gross. So when you are going through this process of choosing and picking your input values, and you have an m value that is also a fraction, again, I would highly recommend take a little bit of extra time of, instead of just choosing any input value at random, I would choose inputs that are multiples of that denominator. And again, they can be positive, they could be negative, they could be 0. It's your call. I just highly recommend that. I think that does make life a little bit easier when you're going through and plotting these things, especially with fractions showing up. And then again, once we have our points, we're plotting those the exact same way as we did with our previous example over here. I'm just looking at our time, and I'm not going to go through that because we did practice with that yesterday, and we have our reference example over here. So this is everything for the 8.2 material with graphing linear equations. I'll end the recording there, and I'll take any questions that you guys have after that.